let me welcome Professor Shannon. Thank you.
All right, good morning, everybody. So this is a workshop that is focusing on energy efficiency. And yesterday I was happy to attend some of the very interesting talks that discussed energy efficiency at the device level. My talk is going to focus on the complete opposite end of the spectrum. I'm going to ask the question, what does it take to build reliable systems? And yes, we build systems out of devices, and therefore if you have energy efficient devices, you have energy efficient systems. So it is true that the system level energy efficiency is totally a function of the device level energy efficiency. However, it is not true that system level reliability needs to be a function of device level reliability. And the reason for that is because we can build reliable systems out of unreliable components. It also turns out that at the circuit, architectural, and system levels, there is a very close tie-in between energy efficiency and reliability. There's a trade-off that goes on. So for example, I could relax the specifications on the reliability of the components in order to benefit from its energy efficiency, and then compensate for this lack or reduction in device level reliability by imposing system level techniques. So stochastic computing takes this view that if you want to achieve both energy efficiency and reliability, one needs to play around with the relationship between reliability and energy efficiency at all levels of the design hierarchy. And so with that, that's kind of a high-level summary of what my talk is going to be. At the end, I hope to have a brief discussion on what are the implications of this system-oriented view on the design of next-generation devices. So I would like to begin with a view of how Moore's law has progressed over the past 4 or 5 decades. Historically, today, if you look at device design and if you look at device research, the goal of all the work that we do at the device level is to come out with what I term as an ideal switch. We want a switch that is on when it is on, and when it is off, we want it to be off, which means that we want the leakage currents to be extremely small, or if you use those MEMS relays that we heard yesterday from Professor King, we would like it to be 0. Why do we want an ideal switch? This begs the question. The reason we want an ideal switch is because the foundations of computing are deterministic in nature. It just turned out that the work done by Turing appeared about a decade and a half before the transistor was invented. In fact, I argue that if Shannon did his work a decade before Turing, the world would be a very different place today. So the Turing machine is a finite state machine. It is the simplest form of a computing element that has certain properties of universality, which means I can implement a large class of algorithms using this particular abstraction of a computing element. And von Neumann then came around and said, well, a practical way of implementing a Turing machine is this von Neumann architecture. And since then, the entire computing area has been working to build these deterministic computing engines. All right? So the Turing machine is a deterministic finite state machine, and everything that we do in this blue box is meant to deliver a computing platform that gives a deterministic behavior to the user. However, if you look at the two extremes, if you look at the origins of the device properties, if you look at the manner in which we design devices, these have statistical origins, statistical physics. So what are we doing at this interface is to suppress these statistics so that kind of artificially we present an ideal switch for the rest of the design hierarchy. It also turns out that if you look at applications at the highest levels, the level at which a user is going to be utilizing these computing platforms, the application metrics are also statistical in nature. We talk about the quality of service. We talk about peak signal to noise ratios. These are all statistical metrics. But somehow, as we move from the applications into the design flow, and as we move from devices up into the upper levels of the hierarchy, there is a switch that occurs on both sides that constrain the design of these platforms to be deterministic. And to me, this is the fundamental reason why designing energy efficient systems has become such a hard problem. And it is the reason why we have hit a wall, a power wall that is commonly referred to in industry and in the general community. So instead, I want to turn this upside down. I want to say that what stochastic computing does is to use, instead of starting off with the Turing foundation, it starts off with the Shannon foundation. So Shannon's seminal paper was published in 1948, where he showed that by using statistical estimation and detection techniques, one can transmit information over a noisy channel with an arbitrarily small probability of error. And that initial insight and his initial paper has led to the explosion of communication networks today. And in fact, if Shannon hadn't done this work, we would today be using techniques such as triple modular redundancy or repetition coding. They'll be sending the same bits over and over again until the bit level reliability comes down to the level we want it to be. In that case, our information rate goes down to 0. Reliability goes up, but information rate goes down to 0. So Shannon broke that bottleneck. Stochastic computing says, well, perhaps we should view computing as a problem of transferring information over a noisy channel and use ideas from statistical inference, such as estimation and detection, to compensate for those kind of errors. So when we take this particular view, we say, well, now our switch doesn't have to be perfect. It can have certain non-determinism built into it. And if that non-determinism results in tremendous energy savings, hey, that's great. I mean, now I have a system in which I have all these switches sitting around, which are probabilistically switching, but at the system level, I can deliver the performance that the user demands. So the user is not going to see any difference, but it's just that my circuit fabric, my architectures are all designed to be statistical in nature. So this is kind of what I call as the stochastic computing or design sciences driven view of Moore's law. And I believe that for this view to succeed, we need device researchers and systems researchers to get together, work together. And in fact, I was glad to see in one of the talks yesterday, Professor King's talk, to see circuit designers working with device folks. I think that's a wonderful step. What stochastic computing demands is to take that interaction level higher and higher up. Okay? John von Neumann, who is one of the founders of computing, had in fact written a paper in 1956. He was concerned about reliability. And in fact, he wrote a very nice paper to address the issue of building reliable systems out of unreliable components, because he made the assumption that switches are not going to be reliable. But right on the front page of this paper, he says that his treatment of error is unsatisfactory. And because the reason, I'm just telling you that the reason it is unsatisfactory for him and for me as well is because it was taking a fault-tolerant computing view of reliability. But then he goes further and says that it should be treated as information has been. Error has to be treated as information has been by Shannon and Zilzard. So stochastic computing does that. As I explained to you what is stochastic computing, you will see that we treat errors as a statistical phenomena. We treat computing as a statistical inference problem. And in the process, we get tremendous benefits in terms of reliability and energy efficiency. I should also mention that today, in one of the Focus Center research programs, GSRC, Gigascale Systems Research Center, we have an ecosystem formed around this core idea of stochastic computing. We use the term stochastic platforms. So it brings together researchers from circuit design, architecture, programming models, as well as information and coding theory to address the problem of designing such platforms. Right? And I should also at this point give credit to Jan Rabai, who was the person who got all of this started in 2003 when he asked me to join GSRC to work on these kind of problems. So that was, the initial work was on a particular idea that I was researching called algorithmic noise tolerance. It has now flowered into this kind of a very rich area of research with lots of implications. And today I hope to share some of those with you. So this is kind of setting all the different components of a stochastic computing ecosystem in front of you. This is still a work in progress. A lot of interesting problems remain to be solved. We in fact have a very solid theoretical foundations on which to base stochastic computing. And it is because it comes directly from the area of communication theory, information theory, and coding theory. What we have done so far is develop such foundations and use them to design stochastic kernels. We have taken application-specific kernels such as those for image processing, error control coding, filtering, motion estimation, and so on. And we have used circuit-level models, spice-level models to see how well they perform. And then we have taken the most promising ones and implemented a series of integrated circuits in which indeed our circuits make errors, but from a systems perspective, it meets the high-level requirements. So we have actual silicon to demonstrate these ideas. We have a number of and furthermore, we have also within GSRC a number of faculty researchers working on design methodologies, Rakesh Kumar, Jayjit Roy Chaudhary, Sharad Malik. And then we have FPGA prototypes, Subhashish Mitra. And furthermore, we have proposals to explore some of these processor topologies. For example, I could use any of these kernels and put together a stochastic SoC. This is something I can see happening in the near term. Subhashish Mitra has another version of a stochastic processor where he has one core which is heavily reliable, conventional, and a bank of highly energy efficient but unreliable processors. And then we find ways to map applications onto these platforms. Okay, so now I want to take a step back and kind of say that the move from deterministic computing to stochastic computing isn't as dramatic as we think. So what I've done is I've constructed a path from deterministic computing to stochastic computing, and I want to walk you through that path. So if you think of deterministic computing as a mapping from an input space, let's have n inputs, so 2 to the power n possibilities, and m outputs, 2 to the power m possibilities. Right? Some of those m may be equal to n or not, but in this case they are. If the mapping is 1 to 1, then it is essentially a relabeling problem. I have an input coming in, there's no change, the output, there's one fixed output for that particular input, and therefore we relabel. It's essentially a relabeling issue. If you take that one step further, a more interesting scenario is when a number of input points or input values map onto the same output value. This is more interesting, more commonly occurring computing functional maps. This can be viewed as clustering. Computing can be viewed as a clustering problem. I have an input coming in, I put it in bucket 1 or bucket 0. Furthermore, there are situations, in fact, if you look at truth tables that describe logic functions, many of those truth tables have lots of don't care sitting there. All right? So today what do we do? When I get an input and there's a don't care, it really means that that input can be mapped to output 1 or output 0. Okay? And because of logic minimization step, I in fact have to select one of those. So when I take these don't cares, I'm actually throwing it away and choosing the one that results in the smallest logic net list. So I could have chosen option 1 or option 2. Both of these are equally fine options as far as implementation of this function is concerned. But I choose one and implement one of those. So when we take this view of conventional computing and say how can we overlay some statistics, some probabilistic mechanism on top of it, it boils down to saying that let's keep both of these mappings in place, but we assign some probability to these transitions. All right? So it is still many to one as before, but it is now a probabilistic mapping. This jump is, at least to me, it looks like a minor jump. All right? Maybe it's not, but to me it looks just like a minor jump. Furthermore, if I bring in application level constraints down to this functional level, then I can create many such mappings, which means I can say that the input x1 can be mapped to a large class of outputs while satisfying the user. The user wants to see a very nice image, let's say. Right? They are using video processing, then a large class of images can actually fit that particular input. So that's what, so in that case, the problem of reliable computing boils down to looking at the outputs, right, and then using error statistics, whatever phenomena makes these transitions occur, right, the statistics of those phenomena can be placed here, can be obtained, and then by using estimation and detection techniques, which I referred to earlier, we compensate for the, generate the final output. And this final output should be within the envelope of expected outputs, right. So stochastic computing is in fact that one step going from here to there, but it is different from fault-tolerant computing in that we are using very sophisticated statistical techniques for error compensation. So very quickly, estimation and detection are two major, huge classes of techniques in which you are always given a set of observations. So you're looking at outputs, let's say 1, 2, and 3, and you want to figure out what is the correct output that generated these. Right? So there's a correct output, but because of errors, you migrate from the correct output to one of these. So you're looking at a number of observations, trying to estimate the correct output. In detection, you do something reverse. You have an idea that the correct output lies in a finite set, right? So maybe you have two choices, and you're looking at an observation, and you want to figure out, given what I see, does that observation belong to set 1 or set 0? That's the problem of detection. Both of these problems can be solved systematically, and there are efficient means of implementing architectures and circuits that embody these estimation and detection techniques. So now the question that is on our mind is that, yes, all of this may sound fine, but you're talking about error statistics. You're saying that you want that probability distribution available to you, to the designer. Where is it? Well, this is an example of how in our work we bring in error statistics. All right. So we use the term voltage overscaling. So because we are dealing with modern day processes, the way we induce errors is by reducing the supply voltage but keeping the clock frequency fixed. So that way I have the same throughput yet lower energy, right? So this is an example of a typical critical path chain, latched at the input, latched at the output. And I know that if I reduce the supply voltage while keeping the clock frequency same, I can observe output errors, logic errors that occur that stay throughout the foreseeable future. So in this case, if you take a, let's say, ripple carry adder, you'll notice it has a path delay distribution with a long tail. And typically we design such ripple carry adders so that the one critical path finishes its computation. Though most of the time that critical path may never be excited. Most likely you're exciting these large number of less than critical paths, right? So when you apply voltage overscaling, you're saying that I'm going to clock it somewhere here so that whenever these other paths get excited, I'm guaranteed an error. But those errors will occur very infrequently. And we can do all kinds of SPICE simulations and circuit simulations, look at various architectures, and we can plot the error distributions, draw a histogram of those errors that are generated by these ripple carry adders. Furthermore, this is a measured result. So we built a chip in 180 nanometer. It's a PN code acquisition chip in which you have a somewhat like an FIR filter, and you clock it at a fixed frequency while reducing the supply voltage, and you notice that the error distribution is visible. So these are real quantities that I can utilize in compensating for errors. So having said that, having laid down the different components of stochastic computing, I want to mention that just as we have various classes of computer architectures, superscalar and RISC and so on and so forth, stochastic computing techniques also fall into large, broad classes of techniques. So one is algorithmic noise tolerance, which I'll spend a bit more time explaining, so I won't spend much time here. Stochastic sensor network on a chip, so we built a integrated circuit implementation of this idea. Soft NMR is taking off from NMR and saying you can be smarter than just putting a majority voter. You can in fact take error statistics into account for error compensation. And then finally a technique called likelihood processing. And this work was in fact highlighted in Spectrum last year November issue. So jumping to the core of the matter, what is algorithmic noise tolerance? So here, I'm taking a main block. This is the block I want to implement. Right? If I didn't know stochastic computing, I would take this and try to implement it in an error-free manner, reducing energy as much as possible. Now, knowing what I know about statistical inference, I'm going to let the main block make errors. So that allows me to make this main block operate at very high levels of energy efficiency. So it will make errors once in a while, and what I really want is this error-free output, why not? So what I do now is I take a companion block, I design a companion block called an estimator. I have to put two constraints on the estimator. One, it has to be small. It shouldn't be as large as the main block, because otherwise it's defeating the purpose. Second, it should not make any large errors. It should make small errors. So those errors are referred to as estimation errors, right? So if I look at the distribution of eta, the hardware error, and epsilon, the estimation error, I should see a profile like this. And this is what we actually see in practice. The black dots, the black stems are the PMF of hardware errors. So when errors occur, they occur with large magnitude, otherwise they don't occur. This is a cartoon plot. And then we have estimation errors, which are small magnitude, but very frequently occurring errors. The error compensation scheme is very simple. I take the output of the main block, compare it with the output of the estimator. If the difference is larger than a threshold, I suspect there is an error here. I suspect a large eta has occurred in the main block, and therefore I'll take the output of the estimator as the corrected output. So I'll put a threshold somewhere in the middle of the two plots, right? And that's a design parameter. I can tune it such that the signal to noise ratio is maximized. And you can show, theoretically, you can show that the uncorrected SNR, that is the SNR of just this output, is much less than the SNR of the estimator, okay, which itself is much less than the SNR of this entire block, the ANT block, which is pretty close to the error-free SNR. Okay? So this is a very powerful result because it tells me that the whole is much bigger than the sum of the parts. And in terms of energy savings, what we have shown is you can handle, these error rates can be quite large. Up to 60% of the time you can let the main block make errors. And the overhead in terms of gate count, not in terms of energy, it is just gate count overhead, ranges from 5% to 20%, whereas you can show energy savings beyond the best possible error-free design to be about 40 to 70%. This is using a couple of these algorithmic noise tolerance techniques. So we have a number of topologies for algorithmic noise tolerance. I don't think I want to spend too much time getting in here. I just want to let you know that each of these techniques is trying to estimate the correct output by tapping into various parts of the block B. Just as an equalizer in a receiver looks at the output of the channel and tries to figure out what was transmitted. Okay, in a similar manner, we treat this B, the block B, as a noisy channel. We tap into it and we compensate for it. This is a chip that is quite an old chip that we designed. The first chip that we designed in this on this topic, in which we had a MAC unit that was implementing an FR filter, and another MAC unit with lower precision, lower clock frequency that was trying to compensate for errors. And a typical plot is shown here. You have SNR on the x-axis and energy savings on the y-axis. So conventional systems without ANT, your SNR drops dramatically. The moment you get errors in a conventional system, everything falls apart. But once you use it in the ANT context, you get significant energy savings. Another example of using motion estimation, where we have an estimator that uses a subsampled version of the image. So the main block uses the standard image, but a subsampled version of that acts like an estimator. So there are many, many ways of designing estimators. And if you have signal processing background, statistical signal processing background, you can come out with a variety of such estimators. And then one has to figure out which of these are in fact energy efficient and effective in compensating for errors. This is a chip that recently was tested as part of our GSRC work, in which we took a PN code acquisition filter and we broke it down into sub-filters, which we call as sensors. So each of the sub-filter output has both hardware errors as well as estimation errors. hardware errors because we overscale each of the sensors, and estimation errors because they are not the entire filter. They're using part of the inputs. So we first showed via simulation that there are tremendous benefits of using these statistical techniques and build up an architecture and then implemented an integrated circuit and compared to state of the art. State of the art in terms of error resiliency works with error rates that are very small. 1 out of 10 to the power, let's say 1 in 1,000 or 10,000 cycles will be an error. Here we are talking about error rates that are very, very high. And yet we are able to deliver the right level of performance that the user expects. This is a more recent work where we use algorithmic noise tolerance in the sub-threshold regime. And in the sub-threshold regime, we studied the impact of voltage over scaling. Actually, scaling the voltage is not as good because your delays are very sensitive to the voltage, so your error rates increase dramatically. So frequency over scaling seems to be a much more kind of a robust way of inducing errors. And these are some of the measured results that we have that show that you can reduce energy beyond the minimum energy point that most of the circuit designers are operating at today. I'll skip soft NMR. I'll just summarize by saying that stochastic computing is about taking application level metrics, statistical metrics, and matching it to the statistics of the nanoscale fabric. And this is my, I would say, my final slide, but this is a point where I hope it can spark some discussion. So as I was preparing this talk, I thought, what can stochastic computing mean? What impact does it have on device design? So to me, in return for energy efficiency, what I would like to say is that we are prepared to handle non-deterministic device behavior. We are used to non-determinism at architectural and system levels. Why should the device be forced to behave in such a deterministic manner? Furthermore, if it is possible to have a average case behavior, right, that is better than the conventional device. So let's say you're scaling devices and you're sitting somewhere here, you have a certain tolerance on various parameters. You're interested in moving that device parameter to another value. But today, you believe that the tolerances have to be kept the same or maintained or made better. What I'm saying is this movement is important, but this variance may be relaxed, because if the impact of this variance is better energy efficiency but less reliability, then at a higher level I have techniques to compensate for it. Low SNR switches. So if there are switches that you're building that kind of have a smaller difference between, let's say, a 1 or a 0, right? A noisy 1 and a noisy 0 are very close to each other. It is okay because I can put an estimator and detector at the output that is going to treat it as a complex communication network and then decode what's the correct output. So low SNR devices, low SNR switches are desirable. And then finally, multi-state switches. So I think of a switch as a state machine. It has an on state and off state today. And in each state, it consumes some energy. And as it goes from state 1 to state 2, one state to the other, some transition energy is being consumed. Well, if I have multi-state switches in which each of the state variables are in fact close to each other, right? It is okay for me because for you, it gives you a lot more design flexibility. You have more variables to play with. And for me, I know how to compensate for loss in SNR. So to me, these are, at least as a first cut, these are some certain thoughts or ideas that may spark some conversations between the system architecture folks and the device and circuit folks. And I was actually fortunate to meet with Dimitri this morning, and we talked about it over breakfast. So one of the implications of this low SNR switch might also mean that the ion to I-off ratios need not be that large. For example, if the difference between, from an SNR perspective, right, from an energy perspective, you definitely want I-off to be small. But from an SNR perspective, if the two switch states are close to each other, it's not a problem for system designers. Okay, so I'll stop here, and if there are any questions, I'll be glad to answer them, or I'll be also around during the break to talk.
that was very fascinating, and I'd like to open it up for questions. Maybe I'll ask the first question. This has been a very attractive option that you have described, yet some people have said that the overhead associated with error correction is such that it would be easier just to make the devices bigger and not make errors.
Right, right.
And so in that trade-off, it's very hard to argue with just making the devices a little bit bigger. So what's your answer?
So I have a very good answer for you. The people who say that are people who design logic circuits, and they are right. But error correction at the logic level is provably bad idea from an energy perspective. They know it, everybody knows it. That's why stochastic computing is not a logic level technique. It is a system level technique. And at the system level, that statement is totally untrue. At the system level, you have more information, you have more, you're dealing with a larger block. And the size of the block is not as important as the error statistics you see at the output of that block. So I can have a large block that is, making errors all the time. I'm not going to go in and correct each of the components. I'm going to focus on the more important points, really the output, the final output, and apply all these estimation and detection techniques. So my argument is make that main block as large as you want, and then put in the error correction circuitry afterwards.
Very
right? Yeah. So all our chips are of that sort. We let the computations occur. We don't touch. We don't go into. In fact, these are all synthesized chips. And it works quite well.
Fascinating. Yeah. Go ahead.
So connecting to that discussion as well, isn't it true that if you sort of grow the size of the design you want to estimate and essentially correct, your state space also increases, right? Not even just looking at sort of a larger ALU with more bits, but really looking at a full pipeline or processor where you actually have many, many states. So your map estimator becomes a ginormous, huge problem simply because there's a lot of built-in state in the system that you need to estimate.
Right.
Can you comment on
Yes.
on
That's
that?
a good question.
Maybe you should explain the question.
Yes. Okay. So the question was, so Vladimir asked the question that if I make the B block, the main block, very large, naturally it means there'll be a lot more states, right? In fact, if I have 2 latches, I have 4 states. If I have 10 latches, I have 2 to the power 10 states. It turns out some of the techniques, not all, some of the techniques, the complexity of detection and estimation depends on the number of states of your block. Vladimir mentioned the map technique. If you use sequence detection, then it's a big problem. My argument to that is before we even hit map, before we even go into map. Map is by the way, for those who don't know what is map, map is maximum a posteriori inference technique, but it's the ultimate performance, it's the best algorithm you can use for estimation and detection. I would not use that in the beginning. I would use the most simplest ones. And the simplest ones do not depend on the number of states. They only depend on the, let's say, number of bits of the output and the error distribution of the output. I will throw away any dependence, any time correlations, and yet I will come out ahead. So it's similar to saying that in the beginning, I don't want to use a Viterbi decoder, instead I'll use a slicer. Even using a slicer is a big paradigm shift for this area, right? But you're right. Once people accept this idea and once we see the benefits, at some point we'll ask the question, okay, how can I bring in a little bit of memory into my decoder or the estimator? And then we'll have to play around with all the nice games we know for designing low complexity, sequence detection type circuits and architectures. So there's a lot of things to be done, but I don't think we are at a point where we are limited by the sophistication of the technique.
Okay, so I suggest we defer further discussion to the break.
Okay.
Thank you very much.
Yeah.
It was very fascinating.